Good morning, everyone, and welcome to the final science breakfast of the year. I want to begin by acknowledging the Gadigal people of the Eora Nation, the traditional owners of the land on which we're gathered today, and acknowledge their elders past, present and emerging. I'm very, very pleased, actually, to say the last seminar will be given by Geordie Williamson, and even more pleased to say he's going to give the seminar on the Fourier transform and its applications. I have to say I am one of the Fourier transform's biggest fans. I taught it for many, many years at Oxford. I used to wear a T-shirt, actually, that had the Fourier transform on the front and the inverse Fourier transform on the back, and it used to say, live life in the frequency domain. It's one of those sorts of in-jokes that very few people get if you're not actually a mathematician. But I will say, if you have ever worked in control theory or estimation or other areas of applied mathematics, the Fourier transform has a long and illustrious history. It's really how the early engineers without computers designed the first spaceships, understood the first signal processing systems, genuinely actually understood the world. And I also think it's interesting because it's genuinely an alternative, orthogonal universe to the one that we're used to looking at, an equivalent representation but different. And it exposes so much of the beauty and fabric of the world in which we live in. So it's wonderful to have Geordie come and give a talk on this. So Geordie is an extremely illustrious, arguably the most illustrious mathematician we have in Australia. He was a graduate of the University of Sydney, and he did his PhD at the University of Freiburg, also a university I've had lots of collaborations with over the years. He currently holds the position of Professor of Mathematics at the University of Sydney and is Director of its Mathematical Research Institute. He is extremely distinguished. In most recent years, in 2016, he was awarded the Chevalier Prize of the American Mathematical Society, the European Mathematics Society Prize, and the Clay Research Award. In 2017, he was awarded the New Horizons Prize in Mathematics. In 2018, he was awarded the Medal of the Australian Academy of Sciences and was elected to the Royal Society. He is currently the youngest living fellow of both institutions. So you are... So I'm really pleased to invite Geordie to talk to us today, and I'm really looking forward to this talk. Thank you.
Thank you very much, Hugh. So I was a little bit concerned this morning. I got an Uber here this morning, and the Uber driver said, "Why are you going to Parliament House?" And I said, "I'm giving a talk on the Fourier transform." And I said, "I'm giving a talk." And then he said, "What are you giving a talk on?" And I said, "Oh, the Fourier transform," expecting him to then ask other questions. And he said, "Oh, I know that. That's where you decompose a signal into its fundamental frequencies, which are given by sine waves, and it's used in signal processing and blah, blah." And I was like, oh my God. Okay. So he basically told me my talk much better than I could ever on the trip here. Yeah. So my apologies if you already know everything about the Fourier transform. So I'm not sure if you've ever been to Korea, but if you have done so, you've probably flown to Incheon Airport. And outside of Incheon Airport is a road. It's called the Magical Road of Anyang. And this is what happens when you drive along it. Okay, so what happens is you're driving your car along a freeway, and then out of the blue, your car starts to sing Mary Had a Little Lamb. Okay. And what is going on, of course, is that they've made strips in the road. You know that wonderful invention that has these strips along the side of a freeway that wake us up when we're falling asleep at the wheel? They've put these on at different intervals along the road to produce a sound which you then play by driving over it. Okay. So this was an idea of the Japanese, which was then done very nicely on this road. So it also illustrates very nicely what sound is. Okay? So I'm going to tell you what sound is. Of course, you already know what sound is, but it's still a little miracle of the world. So we have to imagine that we are sitting here in a pool of air, just like a pool of water here, and every time something produces a sound, what is happening is waves are going out in all directions, sound waves, and they're reaching our ears, these very small vibrations. And we are perceiving this as sound. And so here is, this is a kind of analogy, so here are the sound waves moving out. Okay. And of course we all know this, but it's remarkable. Yeah, these tiny vibrations of the air we're able to pick up. Okay. So here's a picture of a sound wave. The only difference with the analogy with a pond is that in a pond, the waves move perpendicular to the direction in which the wave is moving, whereas in sound waves, the air is vibrating in the same direction in which the sound is propagating. And we are told, as I was told when I was 9 years old or something, that the speed at which the air is vibrating, so this is the wavelength or the frequency, this is the pitch of the sound, this is what we perceive as pitch, whereas the amount of air that's vibrating, this is the amplitude, is the volume. Okay? And I remember when I was about 8 years old, I can remember thinking, oh, that's great, but why do different notes, why is it that when I play a C on a piano and I play a C on a violin, I get a different sound? If that's all there is to sound, why is there difference in sound? Okay. And the reason that I started with this singing road of Anyang is that as we can imagine driving our car and driving across a sound wave, and roughly speaking, our car will then play that song. And this is exactly what happens in an LP record, in a vinyl record. This is an amazing bit of footage done by a Google employee who basically got this new scanning electron microscope and has all these YouTube videos where he applies it to various things. So here, this is a picture of a needle of an LP record tracing out a sound wave which we then hear. So you can see it moving along the groove in the record. Okay. And so that's exactly how a vinyl record player works, and the same principle is being applied when we're driving outside of Incheon Airport in Korea. Okay. So like many things in life, the Americans discovered this idea of the singing road and wanted to turn it into an advertisement. And this is what the result was.
Here's the idea. When you're driving along the road and you go off to the side and you get a rumble strip to wake you up, what if we were able to change those tones into notes and then spread those notes across the lane of a freeway so that when someone drove down the road, it would play a song? We're thinking of the wind till overture. We've been able to calculate the spectrum of spacings that we need for all of the different notes in our songs. Let's drive this thing into a calculator.
So I'm not sure about you, but it actually sounds awful. Okay. And they actually made a very interesting mistake when they built this road. They never admitted it, of course, but this mistake was discovered by a physicist at Caltech. So this road is in California outside of Los Angeles, and he went and drove along it, and realize that it sounds wrong, but it sounds wrong in a very peculiar way. And he came up with a hypothesis, which is in this fascinating blog post called Honda Needs a Tune-Up, which is what happened is that the sound engineers specified, basically you want to place a whole lot of ridges on the road. And the important thing is the relative distance between the ridges. This is giving us the frequency, the wavelength. And it doesn't matter if you're off by a factor of 2, for example. So this corresponds to driving faster or slower along the road. So if you mess up a little bit and you put everything at 1.2 further apart than it should be, then it'll still sound all right. Okay? So this exactly corresponds to just going faster or slower. This means that the frequency is stretched out by a constant factor, a multiplicative factor. Whereas what happened was that the sound engineers said that the distance from the tips of the ridges should be x, and what was actually built was this distance between the ridges. And so they're off by this, the width of the ridges. And so what happens is if you take a song and then you add a constant factor to every wavelength, it sounds awful. Okay? So this was their mistake. And there's some interesting further details here. So they built it outside of a village. It's not a village in the States, it's called a town, I guess. They built it outside of a town. And a number of the residents complained that it was very noisy when all these cars are driving past all the time, right? And so then Honda said, okay, we'll remove this musical road. They did. And then a whole lot of other people complained that they really liked the musical road and could they please rebuild it. And so they did in an unoffensive location further out, away from people that are going to complain. And they made exactly the same mistake again. Right? And this blog post is also fascinating because it seems there's overwhelming evidence that Honda has played with the sound in that ad to make it sound a little bit better than it does in reality. And also that if the ad is anywhere near reality, they were speeding by quite a lot when they made it. Right? So this is what happens when you actually... Oh, this is what we're going for. Just so you know what we're going for, okay? This is the aim. And the reality is the following. Okay. So now I want to come back to the question of why different notes sound differently. Different instruments sound differently. The human voice is instantly recognizable as the human voice, even if it's singing the same note as a violin. So why is this? So it's a fascinating topic because it actually has to do with the physical way that sound is produced. So here is another video from YouTube. So I'll give a list at the end of a link where you can see all these videos. So what they've done is they've taken a violin, they've taken the lowest string, and they've tuned it down quite a lot so it's very floppy. So it's playing a very, very low note so we can see it. And this is what it looks like in slow-mo. Okay. Now what I want you to notice is that the bow is pulling the string across and then it's jerking back. See that? So this is a fascinating topic because the way that a string moves on a violin is fundamentally different to the way that a guitar string moves, for example. And this was a very hotly debated topic, I guess, in the mid-19th century. Exactly how this string vibrates and how it's described mathematically. So what we see, if we see the sound wave of a violin, we can kind of guess the way that the sound is produced. So here you have the pulling. So the string is being pulled, and it's jumping back sometimes, and then it's getting released. So it's getting pulled and released, pulled and released, pulled and released. And you can see that both in the up and down bow sound waves. And it's this characteristic sound wave of the violin that gives the violin its violinness. Okay? I should also say that what else is going on here? It's not that really the string is vibrating the air. So if you just pluck a violin string, if I plucked it here at the back, you couldn't hear it. But this movement of the string is then moving into the body of the violin, and the body is then vibrating enough air that you can hear the violin at a distance. Yeah. Okay, so here you can see it, the stick and the slip again. It's pulling the string. Okay, so yeah. So the physical nature of the production of the sound is what gives it its violinness. Here we see a tuning fork. So a tuning fork is designed so that it doesn't do anything interesting, essentially. So it vibrates in the simplest way. And here you can see it vibrating. So the reason that the tuning fork looks the way it does is in order to vibrate in the most predictable and uniform and easy way possible. And we put it into, or Questacon puts it into a glass of water just because that looks very nice. Okay. So here we have the sound wave of a tuning fork. You'll notice at the start it's somewhat erratic as the tuning fork is struck. There's a whole lot of stuff going on. But the tuning fork is made so that very quickly the vibrations start to approximate what we call a simple harmonic oscillator. And we get that its sound wave looks very simple. So do you know the expression as clean as a whistle? Yeah. So if you whistle, you produce something quite close to a sine wave. And our perception of the clarity of the sound, the cleanness of the sound, is probably where this expression comes from. But if you look on the internet, there is some debate about this. So here we have some more sound waves. So this is a guitar being plucked. So you have a similar pattern where at the start you have some rather erratic behavior as the plucking takes place. And it evens off, but it evens off to something that's not at all a sine wave. It evens off to something that's kind of guitariness. And this is actually my voice. So if you're an expert, you can see that I'm a very bad singer at some point. This is the guitar and the voice. And yeah, the message at the moment is just that it's the different characteristic sound waves that make up timbre, that make us appreciate that something is a guitar or a voice or a tuning fork. Okay. So now I want to come to the first actually mathematical idea here, which is something that is also obvious in some sense, but is extremely important. So if we're sitting here somewhere and you hear two sounds at once, we perceive them as being two sounds. But I want to emphasize that what actually hits our ear is one single sound wave. So I want you to listen very carefully to the following and observe what happens in your brain. Okay. Not a very easy thing to do, but just try. So I don't think any of you thought there's a single sound wave reaching my ear, but I'm separating it out into the sound of a guitar and the sound of someone's mobile that has just gone off, and by the way, I will kill them later on. So effortlessly, our brain separates this sound into the part that is the guitar and the part that is the mobile phone. And what our brain is doing there is something like a Fourier transform. Okay. So basically, the question that we're asking when we do a Fourier transform are what are the basic component pieces of our sound. Okay? So when we add sound, this just corresponds to hearing sounds at once. So I just want to replay this. So the way that we produced this was just literally to take the sound wave of a guitar playing this song and to take the sound wave of a mobile phone and to add them up. Okay? And so you can see. Okay, so what we perceive is much closer to the picture above where I have the two sound waves separate. That's what our brain perceives. And what we're doing is a Fourier transform in some very vague sense. Okay? So what Fourier series is an extremely powerful way to decompose sound and also signals in general. So this is the idea of the Fourier series that, and it's one of the, I mean, for me personally, the two most extraordinary things in mathematics are Fourier series and Galois theory. And years ago, I've given up trying to explain Galois theory, and so I'm left with Fourier series. Right? And it's just an absolutely extraordinary idea that every sound wave can be built out of pure tones. So what is a pure tone? Is basically a sine wave. Okay. And we have some perception of this when we use the phrase as clean as a whistle. But there's another mathematical reason why the sine wave is so special. And it's something that is really remarkable, and we learn in year 9, which is that when you add up two sine waves, you get a sine wave. Okay. It's extremely crucial here that I take two sine waves of the same frequency. So what that means is that if I take two tuning forks and play them at the same time and they're exactly the same pitch, then I just get a sine wave back. So if you're mathematically inclined, it's worthwhile thinking about why this fact is using elementary trigonometry. And it is much deeper than I think I ever appreciated in year 9. Okay. So just to illustrate, so this is a truly remarkable thing. So basically if I write down any sound wave of a certain frequency, the only sound wave that satisfies this property is the sine wave. So there's an intrinsic mathematical characterization of what it means to be a sine wave via this simple property. But it's difficult to kind of convince you that this is really remarkable. So I just want to show you what happens when we get it slightly off. So imagine that I add a sine wave to another sine wave, but I get the frequencies just a tiny, tiny little bit wrong. What happens? Okay. So what you'll hear in the following is a pure tone, a sine wave, and then another pure tone that is of a different pitch but almost imperceptibly so. And then you'll hear what happens when you listen to them together at the same time. So on the slide, you can see the first note that was played, the second note, which is of a slightly different pitch, but imperceptibly so to us, unless you're a piano tuner or something. And then you see the sum, and we get these pulses, this beating. And this is actually a very useful thing in the tuning of instruments. So a piano, for example, has 3 strings for every note. And a piano tuner, once they've got the first string right, they tune the second strings via this beating procedure. So they get it close and they hear these beats. And then their goal is to get the distance between the beats further and further And when it's gone off to infinity, then the two notes are the same pitch. Another way you can think about this is you can imagine the blue and the red line as being two voices. And what this is saying, this fact that a sum of two sine waves is a sine wave, is basically the reason that large choirs sound good. Because you have to imagine that everybody is making little mistakes the whole time. But the goodness, the fact that most of the choir is getting it right most of the time, hopefully, gives us this beautiful sound of a choir. So the successes kind of add up, whereas the failures cancel out in some sense. Okay, I'll go through. And I mean, I do have a bit of music here where I play 3 identical notes and then their addition, but it's not very interesting to hear, so I won't do this. So we have this basic fact that every sound wave can be built out of pure tones. And we can kind of imagine this. You can imagine the following experiment where if we were very, very clever and very careful, we could set up a whole lot of tuning forks at a whole lot of different frequencies and at a whole lot of different volumes. So that's indicated by the size of the tuning forks in this schematic. So that if somehow we managed to play them all simultaneously, it would sound like a guitar. So that probably sounds a bit crazy, and that's also the reason why people thought that Fourier was also a bit crazy when he first proposed this. But that's the idea of Fourier series. So the Fourier series tells us that we can do this. We can break up a sound into its pure tones. But it's also extremely important that we can do so in an effective way. And we do so by by a device called the spectrogram. And you can download a spectrogram on your phone, and you can whistle into it and sing into it and things like that, and see that a whistle is producing a pure tone. And you can think about a spectrogram as being somewhat analogous to a piano roll. So you know these spooky pianos that play themselves? What you feed into this is this piano roll, which has holes indicating which notes should be played and for how long. And basically a spectrogram is saying the same thing, but it's not saying play the notes of a piano, it's saying play pure tones, play tuning forks. And just to illustrate what a spectrogram looks like, here we feed a tuning fork into the spectrogram. So you can see on the left you have a whole lot of very complicated behavior going on, which is the erraticness of when you're hitting the tuning fork. But very quickly you get this dominant yellow line in the spectrogram, which is basically saying that the sound wave is a single sine wave. And as Hugh was pointing out, this picture that we get from a spectrogram is like an alternative view of sound. Extremely powerful alternative view of sound. And not only of sound, of essentially everything that we can measure in the universe. So just an example of the interesting things you can do with the spectrogram. So what I will do is play three sound waves. The first sound wave is a guitar being plucked. The second is, what I've done is I've taken the first 10 major frequencies that show up on the spectrogram. And so this is a little bit like I've taken the 10 most important tuning forks that should constitute the sound of a guitar, and I've just taken that bit of the sound. So this is a little bit like extracting the guitariness from the sound. And then the third sound will be what is left over. So that'll be the pluckiness, the kind of strange stuff that happens at the start that we don't necessarily associate with being a guitar. So here's what it sounds like. This is the original pluck. Okay, it sounds very much like a guitar. In fact, it is a guitar. Here we have the top, I can't remember, probably top the 10 most important frequencies. Okay. So it's sounding like a guitar, but it sounds a little bit more like a computer trying to be a guitar. Yeah? And here we hear the rest. Okay? So I'll go back just so you can hear them one more time. That's the guitar. Here's the first 10 frequencies. Oh, no, sorry. Guitar. Okay. And it would be absolutely impossible to do that without the Fourier transform. So it would be impossible to say in the signal what's the guitariness or something. And just to illustrate the spectrogram again, this is the spectrogram image of the guitar and the mobile phone. And if you zoom in on this, the quality is not great, but you can really see the notes being played by the guitar, and you can see in the middle of it a whole lot of high-frequency stuff going on, which is coming from the phone. And if you look really closely, and I actually did this, you can see the ringtone of the mobile phone in the spectrogram. So. So I just want to briefly tell you how Fourier came up with this idea. And I think that a natural guess was that he was thinking about sound, but he was not at all. What he was doing was thinking about heat. So this is his famous book from 1822. So at that time, people were aware of Newton's laws of classical mechanics, that the same laws that govern throwing a ball on Earth govern the rotations of the planets and the stars. But people were not yet aware of, for example, Maxwell's equations and magnetic fields and electric fields. Okay, so it's at this point in history. And Fourier was absolutely fascinated by heat. So he knew things like if you go 6 meters down under the Earth, you can't really tell by looking at the temperature whether it's day or night. And if you go 60 meters down, you can't even tell whether it's winter or summer. And there'd been various experiments with, for example, heating up a rod. So imagine that I heat up a rod and I make it very hot in the middle, and then I leave it be. So as the rod cools, it will definitely cool, but the temperature in the rod also undergoes a very interesting evolution. So it starts off with a very hot bit in the middle, but slowly this heat disperses out through the rod. And Fourier was fascinated by exactly describing how this dispersal occurs. Okay? And this is the first page of his absolutely wonderful book. It's really, really lovely to actually read this book. So this is I just want to quote from the second paragraph. So like gravity, heat permeates all substances in the universe. Its rays occupy all corners of space. The purpose of this work is to explain the mathematical laws obeyed by this element. This theory will form one of the most important branches of natural science. So he was saying that heat is absolutely everywhere and we have no explanation for it. We have no explanation for how it evolves. I'm also amused by the last sentence because it's very rare to have someone so sure of themselves. But of course he was right. And so what Fourier noticed, and this was his absolutely fundamental idea, was that if I start with a general heat distribution, like that occurring when I heat up a rod, it's extremely complicated to study the evolution of heat in the rod. It's very complicated. But what Fourier noticed is if the heat distribution is of a very special form, then it evolves in a very simple way. So what he noticed is if the heat distribution is given by something like a sine wave, then it evolves just by scaling. So basically it just slowly cools down. And then Fourier made the gigantic leap of saying any heat distribution can be written in terms of these heat distributions for which we can study the evolution, for which we can answer the evolution. So this is exactly analogous to making the bold statement that any sound wave can be written as a sum of tuning forks. And Fourier's ideas had an enormous impact on everything that we do in science. So I want to briefly go over harmony and its mysteries. So why the 12-note scale? I love this because it's a little bit of arithmetic, and it's also something that worried me when I was about 8. I should say that we have Cookie in the audience who's 12. I'm not sure if we have a younger member of the audience today. So this is an experiment that we're told that Pythagoras did. We don't know very much about Pythagoras' life. We're also told that he lived in a cave on Samos for about between a few months and a few years, being pursued by a tyrant. So what he did was he just took a string, apparently, and plucked it, and then he halved the string and plucked it again. And he took a third of the string and plucked it again. He took a quarter of the string and plucked it again. And what he noticed is you get the notes that we generally regard as being harmonic. So the octave corresponds to a half, so that's the lonely goatherd in Sound of Music. The fifth is a third, so what's a fifth? Twinkle, twinkle, little star is a fifth. A fourth is corresponds to taking a quarter of the string, and that's Here Comes the Bride. And a tritone is a so-called devil's interval. So this was avoided in the Middle Ages. This is, I think it's a C to a F sharp on a piano. So this is, for example, the start of Black Sabbath's song Black Sabbath features a tritone. So these simple fractions correspond to harmony. And we actually don't know why certain notes sound so nicely to our ears. So it might be because we've been culturally trained that way. It might be something intrinsic. So one hypothesis is that the frequencies line up. And you can see this very clearly on a spectrogram. So here is, in the middle two columns here, you see a fifth. And you see that a lot of the higher frequencies line up in a fifth, which might be one of the reasons why we perceive the fifth as being so nice. And if in a tritone, you see that this doesn't happen at all. There's essentially no lining up. And this is to do with the fact that 1 over the square root of 2 is extremely poorly approximable by rational numbers, if that means anything to you. There's another interesting phenomenon here, which is the phantom note or the ghost soprano, which happens in choirs, which is if you have a very good choir and the choir sings a fifth, you can hear a magical note in the air. It's almost like there's a third group of the choir singing a magical note. And what is happening is that there's two overtones being produced by the choir that are lining up and that are adding together to produce this mythical note hanging in the air. So I might not go over the circle of fifths. So I just want to briefly discuss a few applications of the Fourier transform. So the Fourier transform is some extremely basic and fundamental observation about the world. And now in science, we apply it absolutely everywhere. And I just want to give a few applications of the Fourier transform. So we're talking about a string vibrating when we're talking about music, or the air is vibrating, and it's essentially a one-dimensional question. And in one dimension, the Fourier transform is about music, it's about harmony, it's about light, as I'll discuss in a second, it's also about waves. So whenever we have a signal which is just a single number, then we can apply the ideas of the Fourier transform to it. In 2 dimensions, we can use it to, for example, for weather prediction. Also for heating plates. In 3 dimensions, it's even more fundamental. So it's at the very base of quantum mechanics, so the so-called atomic orbitals. Astroseismology, the study of the way that stars vibrate. It's also extremely important in 3D computer graphics. And in higher dimensions, this is where I basically spend my days. So this is where my research is. And what we are looking for is always, it's the same question as for musical notes. We're asking, what are the fundamental frequencies? What are the kind of pure tones of our situation? And how can I decompose any signal into these pure tones? And it's a remarkably powerful idea. I just want to give you, so here's an example of the fundamental modes of a drum. And you'll notice that they don't, if you look at the fundamental modes of a string, so you have the vibrating string, and then you have the string vibrating like this, and this one vibrates twice as fast as this one. Okay? And the fact that this one vibrates twice as fast, and then the one with 3 vibrates 3 times as fast, etc., is basically the reason that we have a 12-note scale in Western music. And here you'll notice in these, so this is what happens when I beat a drum. We have different modes, but they're not multiples of each other anymore. They're not easy multiples of each other anymore. And this explains why we don't think of a drum as having a pitch. And these are also extremely important if you're studying, for example, heat distributions on a disk. These are pictures of the strange world of quantum mechanics. So these are the orbitals for the hydrogen atom. And you can see these packets as being, again, like fundamental frequencies of the hydrogen atom. And at Sydney Uni, there's an astroseismology group which studies the vibrations of stars. So it's a remarkable thing that stars form kind of 3-dimensional drums. And you can see how they're vibrating. And I'll just play you 30 days of Alpha Centauri. So you can see Alpha Centauri in the sky. And they've made this sound by looking at the way that Alpha Centauri is vibrating. So you can kind of hear this star. And they compress 30 days down into 8 seconds. So here it is. And finally, I just want to finish with an analogy, which is light and the prime numbers. So, of course, light is also a wave. And we have the visible spectrum, which is some very small part of the electromagnetic spectrum. It's very interesting that we can't see an octave. So the thing that we find so harmonious, the most harmonious thing in music is the octave. And we can't quite see an octave. So it's fascinating to think what an octave would look like if we could see it. But we can see a fifth, and there's no particular reason why we perceive these colors as being harmonious. And I want to, so when we look at this spectrum, what we're doing is we're taking a Fourier transform. So we're breaking this light up into its composite pieces. And there's a remarkable application of this, which is the Fraunhofer lines. So here we have the sun's light, and what Fraunhofer noticed is that there's gaps in the frequency. So he basically shone this light through a prism, and he noticed these gaps. And from this, with some work of Bunsen and others, they were able to determine, for example, the chemical composition of the sun. So the sun's light looks like it's white to us, but when we take a Fourier transform, we notice that there's these gaps. And just by analogy, what we do in mathematics is to apply this Fourier transform to questions of a mathematical nature. So this is a plot of the Riemann zeta function, one of the most famous functions in mathematics. And the zeros of this function, where the red and blue lines are both on the zero axis, are are something like the Fourier transform of the prime numbers. Okay? So we're shining this Fourier transform into the world of the abstract world of pure mathematics. Okay? So I just want to, in the abstract, I promise to explain what this has got to do with Pink Floyd. So I think it's extraordinary that this cover of one of the most famous albums in music has, in fact, a Fourier transform for light. Okay? So thank you very much.
I'm going to get questions.
Yes.
So I'd like to open it up for questions. There is a microphone, I think, going round. Sorry, we've got one down here. Ruth? Just a second.
We've got your cartoon up.
Oh, yeah. This is, I thought I'd show you my favourite Fourier transform cartoon. In fact, I think there is only one Fourier transform cartoon. Sorry. Now you know why it's funny, is the important thing.
Can you explain, how does the eardrum receive so many waves and interpret them all simultaneously?
Yes, so there's a fascinating... the study of actually how the eardrum works is absolutely fascinating. And I don't think that we really understand... So the analogy that I'm using of a Fourier transform taking place is it's an incomplete analogy. So our ear appears to not quite do a Fourier transform. But there's something fascinating. And I should say that I'm sure that you know much more about the anatomy of the ear than I do. But there's something fascinating, which is that there's a kind of cone in the ear which can cut out... so what is it? Which way around is it? I'm not sure if... people often tell you when you're listening to music, you should try to concentrate on the lower notes. And then you can hear everything. And what you can actually see in studies is that when you think about trying to listen for lower notes, something physical actually happens in your ear. And so we have some control of actually cutting out frequencies. We can actually control cutting out certain frequencies by thinking about perceiving certain frequencies within our ear, which I find fascinating. And but the moral is that if you listen for high notes, then you only hear high notes, whereas if you listen for low notes, then you hear both the low and the high notes. Yeah.
So next time you go to a concert, yeah, okay. Sorry, question there.
I wonder, could we go back to the previous slide with all the links? Thank you.
Whoops. I guess that wasn't it? Yeah, there we go. So if you put, if you search for me and then put mhm.html, there's a complete list of links for this talk.
I should take a photograph of everyone taking photographs of the screen. Any other questions? Yes, down here at the front.
What's the most exciting discovery that you've made?
So the most exciting discovery relevant to this talk is it's an extremely difficult question how big these packages of... So in the case of of sound, we can take two sine waves, one a translate of the other, and we can express any translate in terms of these two. This is a rephrasing of the fact that a sum of a sine wave and a sine wave is a sine wave. Okay? So in that particular case, we would say that a particular representation has dimension 2. Okay? So this means that you can express all measurements in a system in terms of two parameters, basically. And an enormously difficult question in our field is to determine how big these packages are in higher dimensions. So in the example of the hydrogen atom, we know that we have a package of dimension 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, off to infinity. Right? And we teach this to our first class in representation theory, this beautiful thing about the hydrogen atom. But when we go into more complicated situations, for example, you might consider frequencies on a very high dimensional sphere, you can ask how big these packages are. And people thought for about 30 years that these packages had a particular size. And I showed that they were just slightly wrong. They should have size like 10,463,000,000, and I show they have size 10,461,000,000 or something like that. It's just slightly off.
Next question, yeah.
I'm in a barbershop quartet, and barbershop quartets are really interested in ringing their chords. And you mentioned that soprano ghost voice.
Yes.
Is that related to ringing chords?
What does it mean, ringing?
So if you get a barbershop quartet to sing, say, a triad,
yes.
So C, E, G, C, if the voices are really locked in tune, the pitches are all where they should be, those overtones, those fifths and octaves that you just talked about, part of the 12-tone equal temperament scale. You start to hear these overtones.
Yeah, this is exactly what I'm talking about with the ghost voice.
Yeah,
The overtones are locking in.
Yeah.
And so you're getting those really strong notes above.
Yeah. And is that related to this thing called the singer's formant?
I don't know what that is.
Okay, right.
Yeah. But I should say, I have a friend who is a very good singer and also a very good mathematician. So if you write to me, I can put you in touch with him. Because whenever I have a question about these things, I ask him.
So do you play a musical instrument out of interest?
I sing very badly.
Yeah?
And I like playing instruments very badly.
Okay,
Yeah.
all right, good. Sorry, question down here. All right, sorry, someone already got the microphone. I apologise. Yep.
You mentioned that you kind of missed the depth of Fourier transforms when you were in year 8, and that excited you. Do you think we're missing a trick with teachers that they can excite some kids?
Oh, without a doubt.
Yeah?
Yeah, I don't think anybody thinks that we're inspiring kids enough with mathematics. And yeah, I'm not sure. I don't have any answers, and people think about this a lot more than I do, but we're definitely missing something.
Sorry, just here. Yeah.
I'm an analytical chemist, and the Fourier transform changed analytical chemistry by allowing us to take spectra very, very quickly. And it's interesting that, so Fourier transform infrared spectroscopy, Fourier transform nuclear magnetic resonance is just taken over. We don't do the other kind anymore. But we always convert the spectra back to what it would have looked like had we have done a wavelength by wavelength job. I've always found that really interesting. We never look at the Fourier transform, even though it's underlying it.
He needs my T-shirt, Live Life in the Frequency Domain. So, sorry, any other questions? Yep, there's a few at the back.
Excuse me. It seems to me that Fourier transforms could be applied maybe to neural nets, to convolutional neural nets maybe. Have you done any work so the classification problem that a neural net works on recognizing your cat, for example, here. It seems like a Fourier transform might be useful in the discrete classification problem underlying. I'm wondering whether there's any applications.
Absolutely. So I haven't gone into discrete Fourier transforms at all, basically through lack of time. But yeah, there's an enormous world of discrete Fourier transform, and that's actually more where I spend my days. And it's enormously powerful. So just for everyone to get a picture, when we're talking about a musical note, for example, we're talking about a continuous signal. But you can imagine, for example, all the states in memory of your computer as being something like a signal. And you can try to do a Fourier transform there. And that's discrete Fourier transform, enormous subject. Yeah.
Okay, last question.
So I'd quite like to go back to your cartoon, Hugh. So I'm assuming that's an acoustic profile of a fairly angry cat. And I'm interested, so acoustic profiling is increasingly used in biodiversity monitoring, so it might be used to monitor populations of birds in a wood or used underwater. Is that using Fourier transform to essentially identify what bird song and perhaps the number of birds or crickets or something?
Fascinating question. I didn't know that this is used for biodiversity, so I'm not sure.
Yes, incidentally. Yep, you can do a whole species identification using essentially its spectrum. Yep. Okay, I want to thank Geordie for a great presentation. And
Thank you.
Book and spectrally clear wine as well. So that brings to a close our seminar series for 2019. This has been the most heavily attended seminar year that we've ever run, actually. It's been extremely popular, so I'm very, very pleased that we've managed to get the right kind of mixture of different types of speakers, great speakers, right across. Of course, we're looking forward to next year now, and our first speaker next year will be Professor Rose Amal, who was the Premier's Science Prize winner this year recently in November, who works in areas like catalysts and chemical engineering, and particularly in areas like renewables and the applications of catalysts to that. So we look forward to seeing you in the new year. The first seminar will be on the 20th of February. Thank you very much, everyone.